Hello everyone, I'm Tung. Now I'm going to present our final project named Forward and Backward Private Searchable Encrypted System with Optimal Overhead. Nowadays, data outsourcing services have become more and more ubiquitous. Nevertheless, outsourcing data to external clouds might lead to privacy concerns, especially for sensitive data. Although end-to-end encryption can enable data confidentiality, it also prevents data utilities, such as querying analytics, thereby invalidating the benefits of data outsourcing services. Basically, people expect that they can perform search queries over their encrypted database in a secure and efficient manner. To address this issue, Searchable Encryption, or SE, was proposed to enable keyword search on encrypted data while respecting the confidentiality of the data and the search query. The user just needs to send a search request to the cloud server where their encrypted data is stored. Then she can receive the match results, and the cloud server cannot learn any information from her data and queries. There have been essay designs that focus on privacy, protecting search patterns, and supporting multiple writers. In our work, we aim to achieve high security guarantees and user efficiency. Our first proposed system includes two servers and an honest user, in which at most one server can be corrupted. Then we also propose another design that includes three servers, where at most two out of three servers can be corrupted and collude with each other. As long as there is one honest server, then the system is still secure. Our scheme achieves semi-honest security, in which the adversary is curious about the user's data and queries, but the servers follow the protocols faithfully. To support keyword search efficiently, besides the file system that actually stores the user's documents, we use the data structure to support search queries, so-called search index as follows. Our search index is a table where the row dimension corresponds to each document and the column dimension corresponds to each keyword. In particular, if a keyword appears in a document, the position of that keyword on the corresponding row of the document will have value 1. To protect the confidentiality of the search index, the user will create additive secret shares of the table and upload it to the servers. For example, we suppose that values are modulo by p equals 32. Then, for a value of 1, the user will create random secret shares of 1, such as 16 plus 17 equals mod 32 equals 1, and each server only stores one secret share of it, and similar for the case of 3 servers. So we just need one of the servers to be honest, then the confidentiality of the search index is still protected. However, this search index design suffers from significant storage overhead if the keyword space is large. To create an efficient search index, we harness Bloom filter as a mechanism to compress the keyword dimension of the table. So, the keyword or column dimension is now called the keyword representation, which is much smaller than the keyword space. For each keyword, its indices in Bloom filter are computed from a key pseudo-random function so that the servers cannot derive which indices correspond to which keyword. Kappa here is a secret key only known by the user. And the position and indices to the keyword are set to value 1. We do similarly for each keyword in the document and for all documents to create the table. Another issue with Bloom filter is that it incurs a certain false positive rate, which is computed as a formula here. For example, with an average of 73 keywords per document, We can choose k equals 7, m equals 2000 to achieve less than one false positive sample on average over a database of 32K documents. With the design that I described, the document update operation works as follows. Suppose that two servers are currently storing secret shares of the search index. For an updated document, the user computes the new Bloom filter representation for the keywords that appear in the updated document. Then he creates secret shares of the updated row, then sends each secret share to each server. Finally, the servers just need to replace the updated row with the indicated row by the document ID. Keyword search in our scheme works as follows. We assume that two servers store secret shares of the search index denoted as M1 and M2 here. First, the user computes the indices corresponding to the keyword using pseudo-random function with his secret key as input. Then, the user sends those indices to the servers. Next, the servers retrieve the requested columns and add them together. Then they broadcast their values to each other. Based on the values of D1 plus D2 here, the servers can know which documents match the search query and return satisfying document identifiers to the user. However, this reveals search pattern to the adversary, as any server can be corrupted. To protect the confidentiality of the search results in the presence of the adversary, we propose a solution that can secure shuffle the results before returning them to the user, such that only the user can recover the final output. So, the secret share shuffle protocol consists of two phases. The first one is pre-processing, which is totally independent with the shuffle input data. There are two parties as described here, in which one party inputs a random permutation pi and the other party inputs a security parameter lambda. After pre-processing, the party who holds permutation pi learns a vector delta equals vector b minus permuted a, and the other learns vectors a and b. In the online phase, we assume that each party has a secret share as input, denoted as D1 and D2 here. Then the party on the right sends its masked secret share, which is D2 plus A, to the party on the left. Then the left-hand side party computes as the formula here and sends the shuffle mask value pi d plus b to the right-hand side party. At the end of this protocol, one party holds a permutation pi and the other party holds permuted output d. Only the one who knows both the permutation pi and permuted output d can recover the actual output. The pre-processing phase works as follows. The first building block is an oblivious transfer protocol. There are two parties in which one party holds a bit B and the other party holds two messages M1 and M0 and M1. Oblivious transfer protocol allows one party to learn the message MB without revealing the value of bit B to the other party, and the party on the right here does not reveal the remaining message M1 minus B. So the left-hand side party can only learn the message of her choice based on the bit value B here. With this protocol, the party on the right can let the party on the left learn a punctual vector as follows. Suppose that there is an array whose elements are the leaf nodes of the binary tree generated from a pseudorandom generator as described here, where S1 and S2 0, S2 1, etc. Here are the six values as input for a pseudorandom generator. Of course, by knowing the root of the tree, any party can regenerate this tree. However, the right-hand side party only sends enough information to the other party so that it can learn that possible positions. For example, on the second level, the left-hand side party can only learn either S20 or S21, and we suppose that it can learn S20. By knowing S20, it can regenerate S30 and S31. For the next level, because there are 4 values, the right-hand side party has to XOR the values of the left nodes together and the right nodes together to let the left-hand side party learn one of the 2 values. We suppose that the left-hand side party can learn S31 XOR with S33 as here, and because it knows S31, it can XOR with that value to cancel out the value of S31 and learn the value of S33. So at the end of the protocol, one party learns a punctual vector, while the other party holds a full vector. So the above protocol can be replicated many times based on the size of the permutation. For example, with a permutation of 5 elements here, the above protocol can be repeated 5 times, such that at the end, one party learns a punctual matrix like this, where the punctual positions are the indices of the permutation, and the other party learns a full matrix as here. Then the party who holds the punctual matrix can compute the values of vector delta as here, where A is the summation of values on column and B is the summation of values on the row. The punctual positions do not affect the value of delta here because the punctual value will be subtracted out in the results of B minus A here, and the other party who holds the full matrix can learn the values of A and B. With 2 servers, we can only allow at most one of them to be corrupted. Therefore, we propose a 3-party secret share shuffle protocol that allows 2 servers can collude with each other, provided that the other server is honest. Pre-processing phase of it works as follows. First, party P1, who holds permutation pi1, interacts with party P2 and P3 to learn delta 1-2 and delta 1-3 respectively, and party P2 and P3 also learn A1 AB1 and A2 B2 during this process. Then party P2, who holds permutation by 2, interacts with party P3 to learn delta 1 and delta 2 prime, delta 2 and delta 2 prime, and party P3 learns A3 and B3 in this process. With those preprocessing materials in the online phase, in which each party holds a set share D1, D2, and D3 as described here, at the beginning, party P2 and P3 sends their mask values to P1. Then P1 computes the permuted output as a formula here, then sends the permuted mask output to party P2, and party P2 computes a new shuffle output, which is grabbed by one more permutation by 2, and sends the permuted mask output to P3. Finally, server P3 unmasks the shuffle output by removing vector P3 here. At the end of the protocol, 2 parties P1 and P2 hold independent permutations pi1 and pi2, and server P3 holds the shuffle output. Only the one who knows both permutations and permuted output can recover the actual data vector D. To realize the proposed design into practical implementations, we face some challenges as follows. First, we need to look into network programming using C++ and how to use some libraries such as EMPOT for efficient oblivious transfer protocol. As we have to implement search and shuffle from scratch, there is no available implementation of that protocol at this moment. And when combining protocols together, we need to debug and test to make sure everything works together correctly. Our implementation is in C++ with EMPOT library for oblivious transfer protocol and OpenSSL for pseudorandom function. We use 0MQ library for network communication between the servers and the user. Our implementation is approximately 1,000 lines of code. Our test environment is on macOS 30.1 with ARM M1 Max 10 core CPU with 32 GB of RAM. Now is our demo. We are showing keyword search and document update operations. First, we run a demo with two servers, where the user sends a search query to two servers, then receive permutation seed from one server and permuted output from the other. From these two pieces of information, the user can recover the actual search output. After that, we run a demo with 3 servers. In this setting, the user receives permutation seeds from servers B1 and B2 and the permuted output from the other. Similarly, the user can recover the actual search output and display it. Now is our demo. First, we are running with 2 servers, so NP is equal to 2 here. So I'm going to launch server S1, server S2, and then I'm starting the client. So it's displayed the average document update time here, and this is a pre-processing phase. This is the actual output. I let it print the actual output on both the server and the client to verify the correctness of our protocols. So this is a time of keyword search, including pre-processing. And now I'm going to recompile the program to run it with third-party. I need to recompile both the user and the client application. Now I'm going to run with 3 server. So now the pre-processing phase is longer because server P1 has to interact with B2, B3, and B2 has to interact with B3 to perform pre-processing. So the pre-processing phase is longer. So now the actual output of the keyword search is still correct. So the client receives 2 permutation seeds from server P0 and P1 and receive the permuted search output from P2, and so finally it can recover the actual search output as here. So we summarize the evaluation of our protocol of our proposed scheme as follows. In terms of bandwidth cost, our scheme achieves up to 3 orders of magnitude smaller communication overhead than state-of-the-art SE designs. Regarding end-to-end latency of keyword search, our scheme is 6 to 496 times faster than existing SEs. In conclusion, in this work, we investigated the limitations of existing searchable encryption designs. Then, based on that, we proposed an SE design that can achieve minimum network overhead while maintaining high security guarantees. Finally, we fully implemented and evaluated our proposed system. This is the end of my presentation. Thank you for your attention.